So in our last class, we started talking about how to visualize categorical variables. And the kind of easy version is if you have a single categorical variable, you just do a bar graph. I think, did we have an example up here? Yes, a bar plot or a bar graph, where each possible category represents a bar, and then you can do the height of the bar in one of two ways. You can either use the number of observations, we call that the frequency method, or you can convert it to proportions. And really, there are rare examples where it may make sense for someone to prefer frequency, but most of the time, the proportion number is the more insightful one. Because our brains are good at working with things that are on a scale from 0 to 100%. And remember, you can think of proportions like percents. They just have to be multiplied by 100. So most of the time, we're going to work with a proportion. But whether you use a frequency or a proportion, you can see on this example, the two pictures look the same. It's just the labeling of the axis that's changed. But changing that labeling, it really does help with the interpretation of the importance of the categories. The other thing to note with the categorical variable is most of the time, the ordering of the categories on that x-axis, that ordering is not important. In the example, it wouldn't matter if you put the own category first or if you put the mortgage category first. There are instances, we had talked some about ordinal variables. Ordinal variables, there tends to be a natural way of ordering the categories. And so if it's ordinal, you probably want to arrange the categories with that natural ordering. But in a lot of instances, it's not going to matter. Where when we were doing histograms with numeric variables, like there you can't go and switch up the order of the bars because they're tied to the numeric axis, like age 20 to 25, 25 to 30, 30 to 35. You can't go and logically put the age bracket 30 to 35 before the age bracket 20 to 25, and then put the age bracket 70 to 75, and then put the age bracket 15 to 20. Like there's an implied ordering when you're dealing with numeric variables. So that's one of the big differences there. Then we talked through working with categorical or cross tabulations. And I have a good example that we'll work on in class today. Beyond, like, some of you may not have done question 5 on the homework. I messed up uploading that question, so I just ended up pulling it from the homework. There'll be a better version of the question as part of the homework for tomorrow as well. So I apologize about that snafu. But cross tabulation allows us to represent two categorical variables. One of them, the categories are the rows of the table. The other variable, the categories, are the columns of the table. And we total the rows often and we total the columns often to get the marginal profiles. Now, if we visualize these, we talked about 3 different plots. A stacked bar plot just means you decide, are you working with the rows or you're working with the columns? And then if you're working with the columns, you take all the different row categories and stack the bar heights for those on top of one another. So that's this first example here. In the table that we were working with, the current home ownership status was the column variable. And so each column gets its own bar, and we look at all the renters who applied for a new mortgage. and we split the bar by how many of them were individual applications, how many of them were joint applications. We do that for each. But the stacked bar graph, or the stacked bar plot, is kind of the least ideal visualization. Firstly, because it's based on counts. And then if you're trying to compare across bars, it can be messy to read. So a better way of doing it often is a side-by-side bar plot. So same idea, just instead of stacking the different categories on top of one another, we just put those bars side by side. So we still have all the rent categories together, a bar for individual applicants, a bar for joint applicants. And the example here shows it with frequency, but it can also be done using proportions. And finally, there is a way to do a stacked bar plot with proportions, but we call it a standardized stacked bar plot, where now each category on the axis was set or was standardized to proportions. So there is a little bit of a loss of information in that in the first stack bar plot, you can clearly see how many people fall into each category. You can see there are way more people with mortgages than people who own, for example. Where in the second plot, they're now all equal to a total proportion of 1. So it depends again on the question that you're trying to answer with the plot. In one of them, in the first one, the stacking really doesn't contribute any information. You can just see the relative importance of whether someone rents or has a mortgage or owns. The subdivision doesn't add any information. The second plot, the standardized one at the bottom, now you no longer have the relative information of how many people have a mortgage versus how many people own, but you can compare the subcategories. So this is the useful one if you're trying to say, if we look at people with a mortgage, we have a higher proportion of joint applicants than if we look at people who rent, right? So whenever you do this kind of visualization, you just want to make sure you're doing one that's appropriate for the question you're trying to answer. There is one kind of plot that tries to capture all of the possible information. And I think it can be very useful, but it can become really tedious and cumbersome to read. And that is something that's known as a mosaic plot. So a mosaic plot starts with a stacked bar plot, but it then adjusts the width of the bars to account for the group sizes. So on the left here, we just have a stacked bar. On the right, we have a mosaic plot. And firstly, if you just look at each individual bar, you'll see the subdivisions are the same, right? Like we have a group called adult, and I know this talks about died and survived. If I recall correctly, this looked at people aboard the Titanic, like whether they survived the sinking of the Titanic or not. So the stacked or the standardized stacked bar plot on the left, it does tell us, if we look at adults, just over 25% survived, which means close to 75% died. And if we look at children, it's more of a 50-50 split. So we can see survival proportions in the adult group and in the child group. But it doesn't tell us whether there were more adults or children on the Titanic. If we go to the plot on the right, it still maintains that same splitting, right? It still shows, if we look at the adult bar, we have about 25% who survived, about 75% who died. But the adult bar is now very wide and the child bar is very narrow. And that's to convey information of, proportionally, there were way more adults on the Titanic than there were children. So the width of the bar, a wide bar here means more adults. A narrow bar means fewer children. So I think it can be a useful tool. It runs the risk of becoming unnecessarily complicated if you have more than two categories on either of your variables. Like a 2x2 is useful. But if any variable has more than two categories, it becomes unnecessarily complicated. Now, I would say a good takeaway from looking at all of these different ways of representing two categorical variables. And if you think back to the different ways we had of representing numeric variables, the takeaway is there are often many ways to construct visual tools of your data, to create pictures that convey something about the data. But different pictures emphasize different aspects of the data. And as much as pictures can add clarity, a bad use of a plot can even make things more confusing. So you want to be careful about choosing a way of visualizing your data. And even a way you can apply this in the real world is if you are reading a news story and someone put in a bar plot or someone put in a stack bar plot, like, ask yourself, why are they using this plot? Are they trying to accurately convey information, or are things being obfuscated through the use of a bad plot, right? It's worthwhile stopping and asking yourself that question before you get all fired up about, whatever it is that you care about, a plot about, government spending, or a plot about illegal border crossings, or a plot about people who open carry, right? There are a lot of things that we have strong opinions about, and we should be careful that we're not just looking at plots that reinforce that without asking why someone is using a specific plot. So there's my little lecture on good use of statistics for the day. The other thing I will say is all of us have encountered a pie chart before. Pie charts and bar plots convey essentially the same information, except that if you have a lot of categories, then it becomes really difficult to read, right? This section of the pie chart it's really difficult to see which slices represent which categories and really how big they are. The context of the example here is not that important. What's important is you can see Some of the information on the pie chart is clearly visible. Other parts of the information, very difficult to see. In general, pie charts are less useful than bar plots, because bar plots, they would separate out all of these categories and you would see them next to one another, and you can often see the how the bars get shorter and shorter. But because each bar is individually labeled on the axis, they're pretty clear. So yes, there may be an instance where a pie chart is useful, but most of the time pie charts are actually not a very good tool. Like there's almost never an instance where you would use a pie chart over a bar plot. And this may be like, you will see a lot more bar plots in this class. I don't know if you're going to encounter a pie chart again. Maybe there'll be one in a homework assignment, but they're just not going to show up, because if we're trying to do good data analysis, they're not an ideal tool to use. And then finally, to conclude this section, we've focused on looking at individual numeric variables, looking at two numeric variables together, looking at individual categorical variables, looking at two categorical variables together. The last thing we are going to just take a minute to talk about is what happens if we have one numeric variable and one categorical variable. How can we see if there is some kind of relationship or association between these two variables? So what we do in that instance is, one of the best tools to use is a comparative box plot. So we separate the data out by the categories. And then for the data from each category, like in this case, the numeric variable, we were able to find all the numeric values for first-year students, all the numeric values for sophomores, all the numeric values for juniors. And then we do a box plot for each different group. So now we can compare the profiles of first-year and sophomore students and juniors and seniors. For example, if you look at this, you could say to me, an interesting feature I'm noticing in the data is it looks like sophomores and juniors tend to have some outlier scores. Or maybe you want to compare the median values. Remember, the medians are these center lines of the boxes. Take note here, the sophomore box, that line is at the bottom of the box. That just tells us there are a lot of repeat values. Q2 and Q1 are actually the same. But, it might be interesting to note here, juniors have a slightly higher median score than everyone else whose median scores are on the same level. So you can often look at these comparative box plots and say interesting things about how the groups are the same or how the groups are different with respect to that numeric variable of interest. So the first problem we have here just starts by giving us a data set and then asks us to do, variations of calculations that we've already done up to this point. So the thing to be aware of is it's important to sort your data set from smallest to largest. And in this case, just conveniently, that was already done. So Median is always the easiest number to find first. You just want to find what's in the middle. It's worth counting. Do you have an even or an odd sample size? We have 1, 2, 3, 4, 5, 6, 7, 8, 9 values. And because the sample size is odd, that means there will be a unique value in the middle. So 1, 2, 3, 4, 1, 2, 3, 4. And what we have in the middle is the 59. So our median, which we also call Q2, that's the value 59. Q1 and Q3 are essentially median calculations. You just want to do it for the lower half of the data and for the upper half of the data. The thing to keep an awareness of is if there is a unique value in the middle, like in this example, that value should be included in both parts of the sample. So when I talk about the lower half of the data, it will be all the values up to and including 59. And if I talk about the upper half of the data, it will be all the values starting at and including 59. And now we just find the midpoint again in each case. Q1 is the middle value 28. Q3 is the middle value 63. So part A was hopefully easy enough. Part B asks us to calculate the IQR, and then we're going to apply that as well. So IQR is defined as Q3 minus Q1. So in this case, 63 minus 28, and that gives us a value of 35. And then we want to identify whether there are suspected outliers in the sample. So we have to calculate two thresholds. These are the whiskers, right, from our box plot. Our lower threshold is going to be Q1 minus 1.5 IQR. So this will be 28 minus 1.5 times 35. And so that's negative 24.5. And there are no values below negative 24.5. So we don't have to worry about suspected outliers on the lower end. Upper end, similar calculation, except we started Q3 and we add 1.5 IQR. So in this case, that would be 63 plus 1.5 times 35. And that gives us 115.5. So the value in our sample, 189, is larger than this threshold. So 189 is a suspected outlier. Now, part C just says, oh, we figure out that 189 was recorded in error. It was not supposed to be part of the sample. Recalculate the median after removing this value. So what are our data values if we remove the median? So I'm just going to copy all of the values except for the median for 189. And now we want to find the middle value again. But note, now we have 8 observations, even sample size, so no unique middle value. So now it splits perfectly into 4 on the left and 4 on the right. Incidentally, that's what you would then use for the Q1 and Q3 calculations. But in this case, we find the median by averaging the two values closest to the midpoint. So 44 plus 59 divided by 2 in this case gives us a value of 51.5. Now, our median before was 59. The median now is 51.5. So the median did change. What was not part of this question was doing the same thing for the mean. If you were calculating the mean as well, the mean would have a much bigger change. So I'm going to cheat a little bit and tell you it changes, but not as much as the mean. And the reason for this is the median is robust, right? It is not extremely sensitive to changes in the data. It is sensitive, yes, in that we can see changes, like going from 59 to 51.5. But it's not impacted as much as the mean would be if we were calculating the mean. Then let's talk about 2.2. I still don't think, sometimes technology is not our friend. There we go. So I think a lot of this question is just interpretation, but there is a calculation part. And so that's primarily what I want to make sure we look at. So you're asked to find Q1, the median, and Q3. Now, again, the median is defined as the middle value. So it's a value that has 50% of the values to the left of it and 50% of the values to the right of it. So let's just go through our plot. The smallest value we have is 0, right? At 0, we have no observations yet, 0%. By the time we get to 10, the height of that bar is roughly 0.35, right? So we would say by the time we get to 10, we've observed roughly 35% of our values. When we get to 20, that bar has a height of 0.25. So we're adding another 25%. So when we get to 20, we've observed roughly 60% of our observations. What about when we get to 30? So there's another bar with height 0.10. So at 30, we've added another 10%. So we've seen about 70% of our observations. Our next bar ends at 40, and that one's roughly at 5%. So at 40, I would say we've added another 5%. And so we would have seen 75% of our observations. And I'm going to stop here. First thing we want to figure out is where the median is. The median is the 50% mark. So we go from 0 to 35 to 60. So somewhere in here is 50% is there. So the median, I do not need a more precise answer than this. The median is in the range 10 to 20, because somewhere in that range of values, we cross the 50% threshold. Now, Q1 is defined as the 25% threshold, and Q3 is defined as the 75% threshold. So where's our 25% threshold? 25% is somewhere like going from 0% to 35%. So Q1 is in the range 0 to 10. And finally, we are able to be a little bit more precise. I know we are just approximately reading off this table, but we get something really close to 75%, right? So we can say Q3 is close to the value 40. We don't have to give a range here because we ended up close to 75%. So this is all I would be looking for here, for you being able to identify a range that includes a possible value. And you'll definitely see something similar to this on your next homework. For parts B, C, and D, you want to look at the shape of the distribution, because there are two things that determine whether you use the mean or the median. The shape, symmetric versus skew, and whether there are outliers present. If a distribution is symmetric with no outliers, then you're going to prefer the mean. If there is skewness or if there are outliers, you're going to use the median. So when the question asks which is better, the mean or the median, you would say the median. Because there is skewness present in the data. Similarly, when it asks if you're going to use standard deviation or IQR, you can just remember the mean and the standard deviation are always wedded together. The median and the IQR are always wedded together. So if you're choosing median, you're also choosing IQR. And the reason would be exactly the same. There is skewness present in the data. And finally, part D asks, which value would be larger, the mean or the median? And remember what the skewness does. Skewness puts values far away from the center. Which measure is sensitive? The mean is the one that is sensitive. So the skewness pulls the mean up in the direction of the tail. And so the mean will be larger than the median, because the median is not that dramatically impacted by skewness. So the mean is in the direction of the tail. It's the larger of the two values generally.